I'm Mirko Consiglio, and I'll be guiding you today through variational quantum algorithms. So, it's a basic introduction, but um, I'll basically start by going through some slides and then writing stuff down, etc. And then I have a small GitHub page where we can all download, work through some VQE problem. Should be interesting for you or something you'll learn. And well, hopefully it works now that IBM is down, as we found out before in Elisa's lecture. So let's move piece by piece. So let's start from here. Okay. So I'm a PhD student here at the University of Malta. I'm just finalizing my PhD, and I did it on basically variational quantum algorithms. Its main application in my case was for quantum many-body systems. However, of course, variational quantum algorithms, as you will learn, have many other applications. And in fact, the speaker following me today on today's lecture, which is Alessandro, will be talking to you, for example, about combinatorial optimization problems. And in that case, they use an algorithm such as QAOA. However, I'll just give a brief overview about variational quantum algorithms, what they are, how to build one, how to code one roughly, and give one prototypical example of a VQA, which was the VQE, slight letter change there, and that would be the variational quantum eigensolver. Now, the ideas that Elisa alluded to is that, or at least she thinks that, for example, quantum advantage can possibly be attained by variational quantum algorithms. Of course, let's say I am of the belief that we have not yet achieved it, even though if you do a quick Google search, you will probably turn up the 2021 paper by Google. That is the attain quantum advantage, which is still a very interesting paper. Now, let's go on ahead. So in this first part of our session over the talk, I'll go over building a variational quantum algorithm. It will use many of the components you have seen of circuit building, even the idea of measuring on a quantum computer. Okay. And then I'll talk to you one of the applications about variational quantum algorithms, in particular the variational quantum eigensolver. So the idea is that you have a problem you've encoded into a Hamiltonian. Okay, so it would be a big Hermitian matrix essentially, and the idea is that you need to find, for example, its lowest energy. So the eigenvalue and corresponding eigenstate with the lowest energy value, and then you will be solving it yourself through GitHub, the repository I created, if it works without IBM runtime. So let's go over building a variation quantum algorithm. So here, this is the prototypical example I will be showing you over here. Essentially, you require simply 4 basic components, ingredients. And you can mix and match, change these, whatever. Of course, as we'll delve along, you will find or possibly encounter examples where they are heavily related to one another. But in this case, I'll treat them separately, as in you can change them however you want. The first part is the A over here, which is the objective function. Now, variational quantum algorithms are based on the variational principle of quantum mechanics. That is, you need something to minimize over. And typically, that will be your objective function or cost function, some quantity to minimize over. Now, once again, in the case of the VQE, for example, this will be by minimizing over the expectation value of the Hamiltonian. Okay, so trying to find states so that when you compute it's the inner product with the Hamiltonian, you will get the lowest number. Okay. Apart from that, it requires one other input to begin the routine, and that is an initial set of parameters, which will make sense in the next part. So if we move over to the bottom, or in the pink area, where you see the quantum classical loop. Now, a variational quantum algorithm, while it just only has the name quantum, it is in fact a subset of the class of algorithms called hybrid quantum classical algorithms. Once again, alluding to Elisa's previous lecture, right now we are in the era, let's say, of what is known as the NISQ era, NISQ, noisy intermediate scale quantum. This means that the devices that we have are currently quite noisy, of a sufficiently intermediate scale, meaning we can't go beyond a certain number of qubits to prove, for example, or to actively use these algorithms that have been shown to you, such as Grover's algorithm. However, we can still do some things with them. And the idea here with a quantum classical loop is we take the best of both worlds. So we do have good classical computers, right? Of course, but we want to use quantum computers to go further beyond that. However, for some things, a classical computer is still very good and very efficient for doing what it does. And in this case, we split the algorithm into two components. One is where we have a quantum circuit, okay, which can be parameterized by this set of angles, okay? You have encountered RY gates, you have encountered C0 gates. So by now you should know what these are, but regardless, if you have any questions, just stop me and ask away. And the idea is that we want to test different parameters to prepare different states to compute different values of the objective function because we intend to minimize it. Part C, in this case, is a small subset of the components of a VQA. And in relation to a basis change, what I mean is what type of measurement technique you want to do. Now, I will only show you one basic measurement technique, as in if you want to measure something other than in the computational basis. So instead of just measuring zeros or ones as intended in the computational basis, you can apply gates beforehand to rotate the basis you want to measure. Okay. So for example, if you want to go from the measuring in the Z basis to measuring in the X basis, you just apply this Hadamard gate over here. And you will still measure at 0 or a 1, but it indicates in the direction of the X basis. Now, the classical part comes in is the last, let's say, ingredient of our VQA, which is the classical optimization. Now, this is mostly, let's say, it's something that stems from mathematics and physics. Okay, there are many optimizers out there, and their intention is to propose new sets of parameters to compute a cost function to minimize that cost function. Okay, and this goes in a loop. Okay, so each time the classical optimizer produces new angles, all right, you will run them in your quantum computer, measure them, and depending on the cost function, it will propose new parameters. And it will keep looping like this until you have some criterion, either a tolerance value or a maximum number of iterations or loops, as we call them. But ideally, at the end of this entire routine, after running the circuit many, many different times with different parameters, you output a set of optimal parameters, which produce the intended state that you want, because at the end of the day, this will produce a certain quantum state, and the computed cost function at its optimal value. So ideally, it's minimum. For example, in the case of the VQE, its energy, as we will see. Now, let's delve into more deeply, let's say, into this. Of course, these are stuff which I have already mentioned. Okay, so we have these four modules: the objective function, parameterized quantum circuit, or PQC for short, measurement technique, and the optimizer. And one, let's say, very interesting paper on just kind of a white paper review on this sort of topic is the one by Barty et al. And it's simply called Noisy Intermediate Scale Quantum Algorithms. And it's practically a compendium of a lot of these variational algorithms, along with much more detail into each of these modules and many others that you can add, remove, tweak, change, etc., etc. So what about the objective function? We can essentially define it as some function that acts on a set of parameters theta, and it computes, for example, the expectation value of the Hamiltonian. However, there are many more other ways we can do this. So, for example, if we have, for example, a Hamiltonian, okay, let's see if this is right. Yep. Yep. Let's show this perfect. Okay. So in the beginning, we have a quantum circuit. Let me see if I can make these lines thicker, actually. Yeah. So over here, for example, if we have a typical quantum circuit, at the end of the day, we're going to be starting with a bunch of zero states, okay? The all zero register, etc., etc. And the idea of what we want to do is produce some circuit we call U, okay? Which contains many different gates, etc. in it, with the intention to produce, at the end, over here, some psi, which is dependent on theta, okay? And at the end of the day, once we have, for example, a Hamiltonian which encodes our problem, okay, which can be any Hamiltonian you want. In principle, it can be motivated physically, can be motivated from chemistry, combinatorial problems, okay? The idea is simply to just say, listen, my function over here will effectively be the expectation value that I measure of this psi at this certain value of theta of this Hamiltonian. Okay? Now, this is the simplest way to showcase this, um, which is written explicitly more over here, with the idea that, once again, this psi is produced by applying some unitary operator or set of gates, they're effectively the same, onto the old zero state. Okay, which I will write in shorthand notation like this. So this means zero state of n qubits over here. Okay, so zero state or all zero state, let's say. Now, however, one big problem we have in particular. Yep, yep, yes, exactly. Exactly. I mean, this is basically the variational principle. The only difference is that you might find it, for example, written like it basically says, sorry, the variational principle in particular, and it stems from this. Should we put it like this? Maybe it's easier. The variational principle in particular is that the energy which attains the minimum, let's say, is going to be this, right? So it's bounded below essentially, or it bounds it below, and assuming that psi is a non-normalized state, right? However, in this case, in a quantum computer, I don't know if Elisa has told you this, but any state it produces is automatically normalized. Okay, in principle, yes, yes, it's called yes, uh, almost, because what you will measure in principle, as you well know, is bits, right? So you reconstruct the state vector. Exactly. You will measure the histogram and you will reconstruct it. You can reconstruct an approximation of the state via measurements outputting from your quantum computer. Okay. However, in the case of testing, for example, these variational algorithms, of course, if you use, I don't know, Python, for example, to run, like, or Qiskit, you can access the state vector because, well, we have full information. But when working on an actual quantum device, what you have access to are bits. Okay. So, the idea is that now, how do we actually, well, we need to measure this, right? How do we measure that? I mean, when I say measure, yes, I have this Hamiltonian, but what is it? How do I write it out in a way that I can measure it? And one way is that most Hamiltonians, for example, can be written in what are known as Pauli strings. Okay, so the idea is that, well, we have the Pauli matrices, right? So here you can write them like this. Okay, so but I will write them like this for ease of simplicity. You can have Pauli strings or Pauli matrices, sorry, sure, the following, which construct a basis of one qubit operations that I can build all my other gates from, right? So, and of course, well, the last one is the identity, which is simply this one over here. Now, all these four matrices I can construct any sort of one qubit operation. And I can construct different gates by taking the so-called tensor product. Okay, so this, for example, forms a 2-qubit gate. Now, the idea over here is that any Hamiltonian, in principle, as long as it's Hermitian and satisfies some other stuff, can be written as a sum of some complex coefficient with some Pauli string. Okay, where pi is basically going to be a tensor from the set of x, y, z, and I, okay, of n qubits. So what that means is each pi will be, for example, x tensor y tensor x, or x tensor z tensor the identity. For example, this means that I have a unitary operation acting over 3 qubits, for example, in this case. Yes? Yes. As long as it's Hermitian. Okay. But we will only mention, let's say, Hermitian Hamiltonians over here because you can study non-Hermitian matrices and etc. Wait, I'm trying to. This is the first time I'm using this software because I didn't think of it before. So let's see what this does. How do I create a new page? One moment. Create a new page. Sorry? .net? Where? This? Ah, this one. Amazing. Thank you for finding that, Giorgio. I don't have chocolate for you, but I guess Elisa left one here. You can take it. Anyway, so let's continue. So basically, this is what we have over here, as in the idea is that once we can construct it into this particular form over here, so or rather deconstruct it into these Pauli strings where we have n of them, okay? The idea is that by linearity, if I want to measure, I have some psi, okay, which is parameterized by theta. Now, theta over here, I'm not writing vector notation, but theta will effectively be a vector of parameters, okay? How many you want in the circuit. And I want to measure this expectation value, okay? And, well, let me write that simply as h of psi of theta, like this for shorthand. By linearity of this expectation operation, this is effectively the same as taking each constituent Pauli string of my Hamiltonian, okay, and measuring each individual Pauli string on a quantum computer, which we can do, okay? If it's infinite, you will never end measuring. So yes, you can, I guess, construct infinite Hamiltonian. Well, technically, there is a finite limit actually to how many Pauli strings you can decompose it at, because the set that I have, if I have a finite number of qubits, once again, because this only makes sense here, I only have the 4 different combinations of strings, and so at most the Hamiltonian, or the size of the Hamiltonian, will scale in the order of 4 to the n, something like this, right? So this is the maximum, let's say. Of course, now, when I measure this, each Pauli string, for example, I have to measure it thousands of times to obtain a decent statistical ensemble of bit strings, okay, that I can then actually compute my cost function and reconstruct it. So in this case, there are, of course, ways and means, for example, to even reduce this number, okay? Because imagine if I have simply 10 qubits and somehow my Hamiltonian utilizes all possible combinations of Pauli strings. If I write 4 to the 10, well, that's a billion, basic. No, yeah, I know. Sorry, it's a million. It's a million, roughly, a million different Pauli strings, and that's not going to be quite efficient. So I will mention this briefly for now, but there are, of course, grouping strategies, what are called, that you can do, where, for example, if I have a commuting set, that means, for example, if I have a Hamiltonian where, okay, it's 3 qubits long, but I have this term, and then some other, well, here I have a coefficient, and then some other coefficient where it's this term. These two strings commute with one another. So what you can do is just measure all in the x basis, and I will explain how to do that shortly. And with the same set of measurements, I can calculate the expectation of both of these operators. So for example, if it's a Hamiltonian written all in x and all in y, okay, then you can just combine these two. And for example, you need only to pass two sets of different measurements. And from the same statistics, you extrapolate the same expectation values. Um, yeah. Now, how do we actually measure, for example, in the other bases? So, well, simply put, if I want to measure in the Z basis, okay, since my, you can say that, let's say the expectation values of going to be of this particular operator over here. What this tells you is that this expectation value of just measuring normally on an IBM will be the probability of getting a 0 minus the probability of getting a 1 over here. Okay, so the number of times I get 0 from measuring 1 bit with the probability of getting 1. Or sometimes you can even write it. Why is this not writing it? We have too many technical difficulties today, unfortunately. Ah, there it is. It's simply going to be, or just twice the probability minus 1, apologies. And the idea is that, well, since I know that the probability of 0 plus the probability of 1 is going to be 1. Well, because of 1 bit, I still have to get 1 bit of output over here. Now, the idea is that if you can initially notice that simply applying, oh, come on. Simply applying a Hadamard onto a Z operator, okay, will change this actually into the X gate, okay? And well, there's a long list of relations you can obtain between Pauli matrices that turn one into another, etc., etc. But the idea is that this tells us that, listen, if we actually prepend our operation, our measurement operator with a Hadamard gate, then we actually rotate our bases into the X bases. And then measuring this will effectively give us measurements in the X bases. And well, this is where we can continue from the slides. If I move slightly forward beyond this and look over here, okay? So simply by just applying either a Hadamard gate, we can rotate to the X basis, or a Hadamard gate follows by the S gate, which is just a simple phase gate, okay? It's another type of gate. And we can measure in the Y basis. So if we have multiple of these Pauli operators acting on different qubits, okay, so what we call Pauli strings, similar to bit strings, then what we need to do is just check what operator it is. If it's a Z, we don't do anything. If it's an X or a Y, we prepend them with some operations. And then we simply measure the output bit string and we get the expectation value of that Pauli operator. And what this long sum tells you is just a nice, well, a simple way of writing out a product of one qubit rotations, and then we get the output of the expectation value of the Pauli term we want to measure. Okay, so this is just one measurement technique, for example. And then I mentioned another idea to add on to your ingredients list is grouping Pauli terms together so that you measure them all at once. So these two combined will give us what we need at the end of the day. Now, before this, however, let's talk about another main ingredient, and that's the circuit itself. So here we talked about how to measure the cost function and the corresponding measurement technique. But what about the circuit? All right, we need a circuit that is able to prepare a set of states where hopefully one of the states is the solution to our problem. And in that case, we need a particular circuit that can search a large space or a sufficiently large space of the Hilbert space where the set of states is contained. So in this case, there are many approaches to building your own parameterized quantum circuit. The first one is, well, this is what I showed you before. So I start in the old zero state and we prepare a quantum state. One of them is what's called one technique, let's say, is called the problem-inspired ansatz. And ansatz is another, in this case, another word I can use for PQC, parameterized quantum circuit, okay? An ansatz is basically a trial state at the end of the day. And this was started by the first, let's say, or brought about by the first paper utilizing a variational quantum algorithm, and they wanted to solve, for example, the the ground state of, let's say, the hydrogen molecule. And in that case, you want to use something which is chemically inspired. And the idea between this, either chemistry or physics, let's say, is that given by Schrodinger evolution, basically, any Hamiltonian can give rise to a time evolution operator, which is the first equation we see over here. So my unitary, given the time t, is effectively the exponentiated operator of the Hamiltonian. Now, the problem we have over here is that, well, if we want to simply create a unitary operator, we do this all the time in quantum physics, right? The problem is that on a quantum computer, it's a discrete machine, okay? By default, the way you even see gates combined, we can't do certain continuous things. So effectively, we have to take this and we have to discretize it. Now, there are of course a lot of different techniques we can do this, but one way, at least taking the continuous limit, is that this is effectively applying one by one these operators over here. Okay? Well, technically, we can even decompose it further where I say, listen, my Hamiltonian, since it is a product, it's essentially the different Pauli strings over here. So I apply these Pauli strings one by one, okay? Alternating. So for example, in my circuit, first I apply the X identity term, then I apply the Z, Y, X term, etc., etc. And then we take this K times. Now, in principle, this would have to, we need to take the limit towards infinity for it. Okay, because this is the only way it's defined in the continuous time limit. However, once again, since we are in a discrete form, we can say we approximate this by saying, listen, let us truncate to a finite value of operators that we apply to our circuit sequentially to reconstruct our problem. Okay, where K is finite. And this is effectively called the Suzuki-Trotter approximation. Or sometimes in literature, you will find it as Trotterization. All right. So what I would do, for example, if I have a typical Hamiltonian in many body physics, for example, which is effectively the Ising Hamiltonian, for example. So over here, I would have some chain of models, okay, some chain of spins, sorry. So it's just the Ising model. So it's just, let's say I can see a ring of different spins, and they can either be up or down, whatever, and we can have hoppings, for example, between a spin up going here. We have a magnetic field pointing, for example, in one direction, okay? The idea is that over here, I would extract these Pauli operators that make up my Hamiltonian, and I would apply them sequentially on the qubits one by one. However, the way I would apply them, in this case from the problem-inspired approach, okay, is by taking rotation gates associated with these Pauli operators and parametrizing them. So in this case, if I take the X gate and I parameterize this, this would be a rotation in the X direction with some value theta. Similarly for the Z gate. Okay? So what we would do, one way to build our ansatz is to apply. Now, I will implicitly not write thetas everywhere here, but you can imagine all of these being parameterized. Well, in this case, sorry, actually, since over here there are two terms, it would be a simultaneous rotation. So an RXX gate for short. This is just basically, let's call this RXX e to the minus I theta. Hmm. Hmm. X is the poly X matrix, yes. Exactly, exactly. So what we want to do is to fine tune that so we can rotate and a finite degree, not just 180, right? But we can rotate theta degrees. And the way you would do that is by taking yes, yes. Okay, okay, okay. That's a fair point. So the Hamiltonian is written in this form. It's a combination of these x gates and h, etc. But we don't know the ground state. The ground state is built up, or let's say, comes about from the evolution of this Hamiltonian. That is very true. But the way we can do this, for example, is that if we want to evolve from the all zero state and simply we evolve, for example, to the ground state of a Hamiltonian, then we would need to sequentially apply here via Trotter. Okay. We need to sequentially apply via trotterization this operation, right? Doing multiple times. However, to speed it up, you can say, listen, what if I take the constituent gates, parameterize them in the sense that I can rotate arbitrarily, and maybe find a faster solution, okay? And the way to find this faster solution, as we will see, is through an optimizer that I'll delve into soon. And you can find it, for example, the ground state in quite a shallow depth. You don't need to go deep that much, where k needs to be a significantly large number in this scenario. It's a fair question. It's a point I skimmed upon. I was just going through it, but the idea is that these multiple, let's say, multi-qubit rotation gates can be simply made by constructing these operators and exponentiating them. Okay, let me write Rxx of theta here actually. And the idea is I can apply these, okay, to how many qubits I have. Let's just take 4 in this scenario. And then my Z gates, since they are independent, I can just plug them in here and keep on going, where this is what we call, for example, a layer. And I can put on how many layers I want. I can repeat this. The idea, like you said, and it's in fact a good point, is that, for example, we only need one layer. Okay, so only RXX in some brick wall structure, what we call, and rotation gates in this access to find some parameters such that it produces the ground state. Sometimes you might need more layers. But the idea, since we are in the noisy era and we need to preserve the coherence times of our qubits as much as possible, we need to find the most possible shallow circuit we can for any problem we have. Okay. Otherwise, well, if we didn't have noise, in principle, we wouldn't need this algorithm. There are, of course, other algorithms like quantum phase estimation, okay, where they use a similar technique to Grover's to amplify the idea of finding the eigenstate or the eigenvalue of a Hermitian operator. So in this case, the variation is a bridge in between. So this is what we use. Yeah. Yeah, yeah. This is just an example, of course. And yeah, yeah. So you're right. I would need since it's yeah. So in principle, since it's yeah, yeah, yeah. So in principle, no, 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 no. It's correct in principle because it's a chain. Okay. Exactly. You would need between 1 and 2 like this, and then you can have like this, and then this goes between qubit one, like it loops around, right? So these would all be RXX gates and then single qubit. So this is what is known as a brick wall structure, because if I extend this, you would find it to be essentially like a brick wall, right? Exactly. So that makes a great segue into the idea of, well, how many parameters do we need in principle? How do we parameterize them? And this is effectively it's going to be a choice for the programmer, for the designer, because all of these variational algorithms require some sort of heuristic decisions to be undertaken. For example, you can have problems where, for example, you encounter difficulties in the classical optimization where you're getting stuck in a local minimum. And that is, for example, because you might have too many parameters, right? But then again, for example, if you have too little parameters, you might not search a wide enough region such that the solution is contained within it. And what I mean by this is that if I imagine my Hilbert space, which is this particular circle, okay, so of n qubit Hilbert space, right? The idea is that if I have an n qubit parameterized quantum circuit such as this one, okay, so this is n qubit, the region to which it can search, okay, for example, might be this region within the entire Hilbert space. Now, the problem with this is that if I add more parameters, I add more layers, this circle, or sort of circle representation, of course, will grow and it will encompass more and more and more and more. Now you say, why not? Well, one problem to say we don't do a very complex or deep circuit, so that is putting too many layers together, is that, well, we have coherence times. We have to worry about the parameters in the circuit because adding more parameters makes it more difficult for the optimizer to find a solution. And well, on the other hand, if our solution is contained here, then this clearly, this area here, means it's not expressive enough. So there's this problem of expressiveness. So how expressive is our circuit? We need it to be expressible enough so that it contains within it the solution, but ideally not too much more that it makes it impinges on our classical resources. Okay. So this is just, let's say, one heuristic measure of how good or bad a circuit is, depending on how expressive it is. Now, of course, here I'm skimping a lot over some details that can, let's say, go in the way of wrong, that it's too expressive. But let's say still not deep enough, but too expressive, where the optimizer problem and not the quantum computer itself. And with that, let's just move into another approach, which we have over here, which is going to be our problem-inspired ansatz. Okay, sorry, not our problem-inspired. Does it not work when I touch it? No. Like this. I'm learning stuff. Okay, so then there's the other approach, which is the hardware efficient ansatz. You have seen, or maybe Elise has told you, that if you want to work on a quantum computer, for example, such as IBM's, there is a set of gates of which the IBM quantum computer can do. And this is given by microwave pulses acting on, for example, these superconducting qubits. And they can do, for example, X gates. Okay, so these pi pulses, they call them. There are also the pi-on-2 pulses. So it's effectively a square root X gate. There's also Z rotation gates to an arbitrary angle. And in fact, in IBM, they are employed virtually. They're not even needed to be done in a hardware manner. However, you cannot arbitrarily do any gate. You need some sort of transpilation. And I believe you have, Elisa must have mentioned this. So the idea is that if I have, for example, a problem-inspired ansatz where even the inspiration of utilizing the physics of the model is, let's say, a good heuristic, the problem is that sometimes it can be too complicated to emulate the model, especially in chemistry models where the Hamiltonians are extremely complex. And in that case, you can use an ansatz or a parameterized quantum circuit, which is hardware efficient. So it uses mostly the gates you find natively, or the basis gates in a quantum computer architecture to build the structure of your circuit. So for example, this is an extremely general way to write it. But the idea is that you have, let's say, once again, many layers of this, where you only use, for example, single qubit gates, parameterized, okay? And you use entangling gates, which are non-parameterized, such as CNOTs, for example. So in this case, you can have a hardware-efficient ansatz that looks like this, which is simply RY gates, single qubit RY gates over n qubits, and then a ladder of CNOTs, okay? And the idea is that you are alternating between parameterized single qubits and then an entangling layer. And then you repeat this many, many times. And this is not inspired from any physical Hamiltonian or Hamiltonian. However, it utilizes are in principle easy to implement in your hardware. Okay. And for example, in the last case I showed you over here is just basis rotations, whatever, just to give an example. But the answers would end prematurely when you have L amount of layers. Of course, this is another approach. Why don't we use only this one? Well, for example, it can be seen that, an extremely difficult proof, it can be seen that if you do enough of these, they turn into what is known a random quantum circuit, as in they become sufficiently random. And that randomness causes the space where you're optimizing to flatten. And typically optimizers, in order to minimize something, as we'll see soon, they require some sort of evaluation of a gradient to move into the direction where I'm minimizing the cost function. And so, for example, it was shown that these circuits also have their own disadvantages. So, of course, the heuristic success here depends on trying to find the best combination of trying to be using problem-inspired answers with being as efficiently implementable in that architecture as much as possible. And of course, each architecture is different. If I look, for example, at trapped ion quantum computers or Rydberg atom quantum computers, or nitrogen vacancy centers, they all utilize different basis gates, so to speak. Okay, but this is at least the two main classes of answers you can use. Yes. So, for example, in the case I showed you, those RXX gates, they can untangle. For example, since I'm acting on two qubits, it's not necessarily that acting on two qubits necessarily entangles. But it is an untangling gate at the end of the day. It means there is a certain value of theta for which you can produce entanglement. Okay, and yes, entanglement is generally needed to find a ground state, just because, let's say, most ground states you can find are entangled to some degree or another. Now let us move on. This I briefly spoke about. What about a classical optimizer? Now this is the only classical part that we enter here in our in the set of ingredients we have. And once again, there are two main classes of classical optimizers. First of which there is the gradient-based approach, which is the one I just mentioned now. And this is used in principle even by obviously normal cost functions. I mean, this is used a lot. For example, when I say combinatorial optimization problems, there are many real-life world problems, such as, for example, in finance, portfolio optimization, or you have the traveling salesman problem, where you have a salesman going around in a city and wanting to find the best route. Okay, you need to minimize some sort of function. And well, these approaches were based back in the 70s, 80s, etc. The idea is that if I want to minimize my cost function, the idea is that if I'm in a space in a particular landscape, I should move in the direction where the gradient points downwards. Okay, so the idea is that here I'm going to be taking a simple scenario, so a 2D scenario over here, where, for example, I have only one parameter. Actually, let me not call it x, let me call it theta to keep in t. And I have my function. And the idea, this can be some sort of function like this. And the idea is that if I'm in a point here, for example, so my initial set of theta 0 at time at iteration 0, we call, was over here. Then the idea is that we would compute the gradient at this point, which would give us some sort of vector pointing downwards, and at the next iteration at theta 1, we would end up downwards. And this would move downwards until it settles into, for example, the global minima. Of course, here there is something known as a local minima, where we can get trapped here, for example. And similar to what I told you about hardware efficient answers, the idea is that in for example machine learning, there's this idea of the curse of dimensionality, where you have, for example, many local minimas, and you can get trapped easily. In this case, what hardware efficient ansatz can create is what is known as a barren plateau. Now, this I don't want to waste too much time into it, just because we could spend another 3 hours talking about barren plateaus. But the idea is that you can have, for example, a large region of the space which is flat, and then your minimum would be a narrow gorge which drops significantly like this. The idea is that if I'm over here, the gradient is effectively zero. And so the optimizer cannot recommend me a new direction to move in. Okay. So this is what is known as a barren plateau. And this is what is known as a narrow gorge. And this is problems that can occur when using highly expressive ansatz. Okay. So this is one of the drawbacks, of course. But once again, if, for example, I use problem-inspired one, I can get into coherence problems. So much of it is a heuristic, and it takes some experience to find, let's say, the best approach to this. So how do we actually compute the gradient in this scenario? And the way we do that, well, simply, is that what I can do is either take a finite difference method, okay, which is shown over here, by simply taking some epsilon value of a very small value and evaluating the gradient at two different points for each parameter I have, and estimating the gradient of each parameter in this manner, where here this delta I over here is with respect to the parameter. And you can do this for all the parameters and then update them by moving in the direction of the steepest descent. This eta here is called a learning rate, and this can be set or tweaked, either fixed throughout the whole optimization, or even you can change it at every iteration, and this signifies how far you move along the gradient. If I put it too large, then I might skip over my entire optimization landscape. I put it too small, I'm not moving fast enough, and it will take me more iterations. However, there's something which is very interesting, although I won't enter into the derivation here because it can take us some time, but because we have such well-structured, let's say, rotation gates based on the Pauli matrices, the R, Y, R, Z, and the Rx gates, there is something what is known as the parameter shift rules. And what this means is that the gradient of a single qubit gate is can be computed exactly, not approximately, by using a finite shift. And for example, in the case of RYRX and the RZ gates, now I know it looks similar, but it isn't really. But if I put a finite shift, this epsilon here, which should be in reality very small, and I put it to pi on 2, okay? And here I prepend the half, I can actually measure at 2 points and get the gradient exactly. Now this is it looks very similar to finite difference, but it isn't, okay? It's still a finite shift, but it's a specific amount. And you can, of course, changes to affect even multi-qubit gates. Of course, the equation wouldn't look exactly the same, but just because they are simply sinusoidal functions and other stuff, we can get the exact gradient to compute, and you can do this for every parameter. Now, of course, this is a gradient-based approach. There are, of course, gradient-free approaches, and well, first thing you might tell me is that do these not suffer from barren plateaus in this case? Well, I hate to spoil it to you, but sometimes they do as well. But they have certain advantages, and also, of course, once again, disadvantages. After all, we need a lot of heuristics for this, although it does work. The idea is that there are many different methods I could go through. I am going to select an old one, but it's a favorite of mine. And I won't go through the equations here just because it would waste a lot of our time. But the idea is that if anyone knows what annealing is the idea of annealing molten metal. Okay, so that means changing it to or letting it settle down into a shape where it is stable enough. Okay, basically. So the idea is that this generally simulated annealing approach does not utilize gradient information at all. What it does is it tries to mimic some sort of annealing strategy based in nature. And the idea is that, let's say we set an artificial temperature. Now, in an annealing process, something that is really hot will cool down over time and it will settle down. What this temperature defines is effectively a probability distribution that if I'm at a certain point in my landscape, okay, let me simulate this quickly. Or actually, I think there's a very nice um, figure on Wikipedia actually, generalized simulated annealing, that actually shows it of how it works. Let me do this quickly. So it's over here. And it should, for example, in this case, we want to search for a maximum. And what it does is it keeps on hopping between different points. And it only accepts to move at that minimum. For example, if it is a certain probability, if basically I throw a die and I get a certain probability of it happening. And this temperature decreases. And what that does is it decreases the probability of moving to a state with a higher energy. In general, it is always accepted when you move to a lower energy. What I mean by this is that, let me create a new page. Let's say I have once again this sort of structure over here. And I start at this point. I will propose a random new point somewhere next to it according to some probability distribution. Let's say it's over here. If the energy of this is lower than the energy of this, I automatically move here in the next iteration. Okay? And I check it again. And let's say, this is actually lower. So I will move here because I'm more comfortable here. I have less energy. But what if it is higher? What I do is, according to some probability distribution that is dependent on my temperature, I pick a random number. And if, well, I get within a certain threshold dependent on that temperature, I say I move here. And then I check again, and for example, I check it over here and say, this is lower, and I move here. And funnily enough, this was proven to show that it can actually converge to a quite sufficient minimum, even by just this seemingly random procedure of hopping between one point or another. Sorry? Yes, it's a it's a global optimizer in the sense that it does not, let's say, prefer one minimum to another just because, well, it's within a certain gorge. So you should find a minimum close to the global. However, for example, while sending here, you could supply it with a local optimizer, a gradient-based one, to even push it further downwards. For example, once you escape the minimum over here, etc. There are many different techniques that you can use both on this. In fact, yes, there are many different strategies of mixing a global and a local optimizer together to fine-tune your approach. Qiskit itself has an entire repository based on optimizers, both local and global, as well as even quantum-inspired ones. Okay, so ones which use, for example, the geometry of the Hilbert space to push it in the right direction based on the gradient. Okay, so of course, this is just some approaches that I would like to show you today. So once again, to conclude this entire chapter, let's say, another example, for example, whether you use just simple gradient descent or stochastic gradient descent, where the difference between these two briefly is that gradient descent will calculate in general the gradient of each and every parameter and move in the direction of steepest descent, whereas stochastic will simply pick a random direction to evaluate the gradient. So if you look at this as a hill and you're trying to go down, the stochastic gradient descent is like a drunk man going down. He still goes down, but he just takes some more detours, basically. Now, once again, to show this figure and to combine it all, we have seen many different components and applications and even heuristic approaches to building the objective function, the parameterized quantum circuit, the measurement technique or the basis change, and the classical optimizer to construct a heuristic algorithm. So I have already mentioned some applications for variational quantum algorithms, but let's go into some more just very briefly. This is a figure I put, in fact, together for my PhD thesis, which was submitted a week ago, so it's quite fresh. But they have many applications, including for dynamic simulations. Nowadays, error correction, compilation, so that means for circuit compilation. They are also used in machine learning just because, well, you can even embed a neural network, for example, in a parameterized quantum circuit to either act as a classifier for classifying data or even generate new data, such as probability distributions, which can be accessed by just looking at the bit strings. At the end of the day, when you measure and see multiple bit strings, they are a distribution. In quantum metrology and even quantum foundations, combinatorial optimization, I put only a small note there, but it's in fact a big chunk of the application of VQAs. And Alessandro, my colleague, will be talking about it in the next session, quite in detail. And then there's also mathematical applications, so trying to find systems of equations, factoring such as Shor's algorithm, search algorithms, principal component analysis, okay? But my main, let's say, aim was on finding ground states. Now, of course, you can have quantum chemistry problems, condensed matter, you can have atomtronic circuits, etc., etc. My focus was mostly in many-body physics, but I will show you one way just to simulate or to solve the hydrogen molecule. So what we will be doing now, very briefly, is that we will take a particular Hamiltonian, and you can see over here that it is written already in Pauli strings with some coefficient. Okay, so you can see the terms here, yx, zi, zz, xx, with some coefficients, and this is a hydrogen, very simplistic hydrogen molecule written in a Hamiltonian form using Pauli strings in a 2-qubit format. And this is where the hydrogens are at a certain, let's say, distance away from each other, because if the hydrogen atoms can move or change, the Hamiltonian will change as well. And let's use, for example, a hardware efficient answer. So here you can see this is taken directly from Qiskit, and I will show by going into the code. We have Ry and Rz gates, each with different parameters, and a simple entangling gate, which we use as a CNOT, and we layer this 3-4 times. And this we will use it to find our solution. So with this, I have created a quick GitHub tutorial. If you want to follow me in this, you can take out your laptops or whatever, or I can simply go through the procedure over here. But the idea is that what I have prepared for you, and I will share these obviously at the end, is that over here I have created, this is rather than a notebook, more an almost essay on introduction to variational quantum algorithms. Ah, look, the text is dancing. Amazing. And I promise I did not intend for this to happen. Ah, perfect. So the idea is that I even delve here into what is, for example, computational complexity theory, the different classes of computational algorithms, the idea of variational algorithms, and even here what we went through is just building the variational algorithm, but in even more detail than needed. However, there is a tutorial-esque part of this, which is going to be running the VQE. So would you like to try, anyone here? Would you like to log into GitHub? Does anyone know how to use Git, basically? Let's start from there, okay. So I'll give you a few minutes for now. So what you need to do is basically, yeah, I should have put it in this slide, but let me go over here, and the link is easier written. Here. So if you just go github.com/Mirko Consiglio/VQA tutorial, VQA_tutorial, sorry. Yes, yes, yes. Ask me any questions in the meetup. Yes. Mm-hmm. Yeah, yeah, yeah. So how to? Yeah, yeah, yeah. Of course, of course, of course. Yes. So the idea is. Yes, 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 yes. At the end of the day, to generate, it's well, it's an energy. Yeah, yeah, of course, of course. So let's say if we want to just simply I mean, can just take some Paulising because you can repeat this at the end of the day. Um, let's say we had already transformed this into basis states and we get some resulted output bit string. So you have, for example, if 0, 0 is going to be, let's say, out of 1,000 samples, for example, you have 236. Then I have 0, 1, which we get, I don't know, 412. 1, 0, we get, let's say, it's 148, so 52. And then 1, 1, we get, I believe that's 100, no? Yeah, yeah, quickly, just to make some numbers. No worries, no worries. 300, exactly. I know it was 100. Amazing. So we have this distribution. The way we want to calculate this expectation value, so is that so this distribution will give us, well, up to some phase, will effectively tell us, listen, the probability of measuring 0 will be 236 over 1,000, right? And then for the rest, we get this value. The idea over here is that I can suppose that my state is simply, well, the square root of these values, right? Or let me simply do square root p0, 0. Yes, yes, it's an amplitude at the end of the day. Okay, so this is just a way of encoding it in a way which is probability amplitude encoding. Of course, over here in reality, there could be some phases which we are not measuring, but they don't affect here our probabilities. What we need to do is simply is say, listen, if my idea that once I rotate into the right basis, the expectation of getting, for example, x on the 0 qubit to be the probability of getting 0 minus the probability of getting 1, right? Now what happens? Excuse me. What happens if I start with this state in principle and I do this tensor product, but I shift then after mapping with h x h tensor s h y h s dagger, this form will turn it into this gate, right? Well, this gate, it's what I meant to show is that this will be 1 minus 1 minus 1, 1. Okay? And this, so once I apply the mapping, this will tell us, listen, if I apply this to my measurement, it's actually going to be the probability of measuring 0, 0 minus the probability of measuring 0, 1 minus the probability of measuring 1, 0 plus the probability of measuring 1, 1. And so I can compute all these probabilities, okay? Evaluate the expectation of this, all right? And this is simply the expectation value over here. And the way I do this, then I just, if I have more of these terms, so if my Hamiltonian is made of some coefficient x tensor y plus some coefficient uh, x tensor z, etc., then I take all of these expectations by shifting them into the z basis and measuring these operators, okay? And I would get a sequence of probabilities that I sum together with the resultant bit strings. Okay, so this is the way, or internally, how it's done when you supply it to a VQE algorithm. Um, of course, there are, let's say, more complicated ways of measuring. So, for example, if yeah, yeah, yeah. Do you have any questions about this? Is there anything unclear or perfect? All right. So, did anybody download the GitHub? Did you follow the instructions on GitHub, or is there any issue that I can help you with, maybe? So. Okay, who here has opened GitHub so far or downloaded it locally? You, Georgia. You as well? I mean, the idea that you can work it out and every time you run it over here, it will be different, okay? But the idea is just to show you one particular example of just a working notebook, which I believe shouldn't require you logging into the Qiskit service right now because apparently we noticed they were unavailable until 6 p.m. tonight. But the idea of what we want to do is that if we have a simplified hydrogen molecule over here, we can write it as a combination of Pauli operators, okay? So this YZ, ZI, ZZ, XX, each with their own individual coefficients, okay? And we supply a parameterized ansatz. So over here we have the Hamiltonian, what we need to measure, and the PQC. And then we need to prepare it for quantum execution. Now, in principle, you don't need to run these codes as in you don't need to transpile it in the sense when you are running on your own local computer because, well, we don't have this idea of basis gates and whatever because we can run what we want. But we need to do it when we want to run on an actual quantum computer because this, for example, code, the IBM quantum computers can't instinctively or natively run RY gates. They have to decompose them into other unitary operators written in their basis gates, which can create this RY operator. However, in this case, we don't need to worry about it. So this code is just a way to make it compatible with us. And in our case here, the decided not to render. But the idea is that if we have this variational principle, then our cost function is simply the expectation value of the state generated by the circuit, our ansatz, which we have done so far. And the minimum ideal is the lowest ground state energy. And so what we do in terms of Qiskit is we define this cost function, which takes in a set of parameters, our ansatz, our Hamiltonian, and this estimator, which is what Elisa showed you, I believe, in the first lecture yesterday. There are two quantum primitives in Qiskit. One is an estimator, one is a sampler. The sampler is a way of doing what I just showed you here by taking these, well, it will give you these bit strings. The estimator will then calculate these shifts or not shifts but basis changes and then work out these probabilities to give you an estimator for the expectation value. Okay, so it is inbuilt within it already, and the idea is that I create this ansatz by feeding in this not tuple but tuple, I guess, of an ansatz Hamiltonian parameters, and I estimate it, get the energy, and I return this energy. Now, this is what I feed into my optimizer. So in this case, I will use the Kobila optimizer, which is gradient free. But there are many more optimizers I will show you. There's from SciPy and Qiskit itself. I initialize a random set of parameters, x0, in this case it can be theta, it doesn't matter what it is. And here I say, listen, give me a vector or a random uniform vector between minus pi and pi with how many parameters I have in the circuit. And what I do is I create this estimator, set a number of shots each time to measure the different Pauli operators, so 10,000 shots per Pauli operator, and I will put it into the optimizer. This optimizer, every iteration, will give me the current energy. Now you can see it, for example, sometimes increasing, sometimes decreasing. All you will see is a bunch of numbers until then out it spits a lot of different results. So first is function, so the minimum function it attained by moving in some certain way, okay, to try and minimize this function. Jacobian here will only be shown if it is a gradient-based method, typically. Okay, so the Jacobian is effectively the gradient of my cost function. The number of function evaluations, so that is how many times the cost function was evaluated on my quantum computer, 140 times. Number of iterations, number of Jacobian evaluations, these are none, whatever. And finally, the list of angles, the list of thetas, one by one, that need to be supplied to the circuit to give me the lowest energy. So the ground state, effectively, if I have attained the global minimum. However, how do we know, well, so sorry, this is the plot of the energy decreasing, as you can see, over a number of iterations. But how do we know that we found the right minimum? There are many means in the case of when using classical problems as in or problems which can be understood classically. So far, if we are doing small problems in this case, we can simply, well, diagonalize the Hamiltonian and calculate the minimum by using some diagonalizing technique, okay? You can see that the minimum over here is achieved. However, right now, one idea that might pop to your head is how do we do this when the problem is so big that we cannot diagonalize the matrix? I mean, the variation quantum eigensolver is intended to solve for this. And of course, that is a current, let's say, big research problem that we have in variation quantum algorithms. There are some techniques that tell you whether or not you are at a particular eigenstate, and that is by, for example, checking the variance, which is a let's say a second order problem in this case, because you also need to calculate the second moment. But that's something we can discuss later on. And well, here I have different types of codes where you can, for example, here in Qiskit, provide different optimizers. And I told you there are a lot. So I will show you, for example, a very simple list of local optimizers that Qiskit itself supports. Some of them are gradient based. Some of them are gradient free. Okay. So for example, the stochastic gradient descent method I show you is one particular, which is called SPSA, which is a stochastic method where the gradient is evaluated in a random direction every time. And this helps, in fact, by somehow saying, listen, if I evaluated the gradient at a random direction, I'm producing noise, right? But somehow the noise of this coupled with the average noise of a quantum computer can actually help it to perform better than just by using a typical gradient descent, okay? Um, so what you can do is play around with this code on GitHub yourself, that in the end you can just here replace any optimizer you want and see how it performs. You can also test by providing different initial positions. So over here, I'm supplying different angles randomly. You can start from a particular example yourself. So you can, for example, set all parameters to 0 and see what happens. Okay. So this is one way you can approach the situation. There are, of course, many other different algorithms that you can apply to this. And in the next session over here, there will be Alessandro who will show you how to work out QAOA, which is an acronym for Quantum Approximate Optimization Algorithm. And it works very similarly to VQE, but the slight difference is that it tries to follow what is known as the adiabatic theorem. So the idea is that you slowly move towards the solution in a well-structured way. In fact, the answers that you can find in QAOA can be put into the class of problem-inspired approaches, essentially, because it is an alternative variational quantum algorithm approach. However, instead of just using, for example, the cost function over here for energy, you can even use it to prepare certain states. So not just ground states, but for example, thermal states. So this ties in well with quantum thermodynamics, where you can introduce, for example, some sort of entropy calculation. All right. So with this in mind, we can stop a bit early. Do you have any questions for this? Yes, Seven? The schematic of, sorry? Ah, yes, 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 yes. Over here, I can actually go on this one. Yeah, yep, yep. You didn't understand, sorry? Ah, well, if I want to measure in a different basis, okay, than the computational basis, I first need to rotate into that basis because I can only measure in the z direction. In the case of a quantum computer by default, let's say, or just the normal way, I can only measure in a certain direction. So if I want to, instead of looking in the up and down direction, I wanted to look into the X direction, for example. I first have to rotate my qubit that way, and then I measure in the X direction. And because my Hamiltonian, when I deconstruct it into a set of Pauli strings, sometimes I don't have, most of the times I don't have components in solely one direction. I have components in multiple direction. I just split it into, or write it down in a basis which covers all directions, the X, Y, and Z, and the I. And there I can just look at these directions basically and compute it. Now, I mean, there are other techniques, for example, like which don't typically use this rotation of expectations, are just what is known as classical shadows, which, for example, try to estimate certain properties by measuring lots of times in um, many directions, including this, but trying to build a statistical distribution for which to infer future, for example, expectation values in this case. So there are other techniques which can be employed. And I would highly suggest, if you have the time, to just, if you want to learn more about this, is just to look at this particular review paper. Of course, there are others like this. This is just one which I found, let's say, quite convenient for me when I was writing my PhD, and it's approachable in the sense that it goes through step by step. Of course, there are other books you could learn about quantum computation in the more general sense, where there's not variational quantum algorithms specifically, which is Quantum Information and Quantum Computation by Nielsen and Schwang. I don't know if this was mentioned by Elisa, but it's a very, very, very good book. And Elisa before mentioned that she thinks that this will possibly, let's say, attain a quantum advantage. We have seen significant improvements over the years when it was first proposed in 2014. So this is quite a recent science. It's only been, let's say, 10 years since it was. Let's say the idea was there prior to this, but it was only in 2014 we saw a real life application of a VQA potentially being used. Now everybody's trying to plug in a VQA every time they see a new cost function just because it's fun at this point. So you can experiment a lot with this. You can try to have heuristic ideas, but there are some set examples such as these guidelines of utilizing, for example, a problem-inspired approach with a global optimizer, and you combine and see what works best. Any more questions? Yes, this one. Ah, this one you mean? Of course, this is my way of explaining it. There are many different ways you can explain this. I try to go the route where it's so I'm a physicist, let's say by my bachelor's, but I was always more attuned to the idea of programming, so I like to talk in bits a lot, just because I find it much more convenient somehow. Even though this is you could in principle not learn any quantum mechanics and still code a good variation quantum algorithm, but having the benefit of both always helps in this scenario. Yes, this session is recorded, and all these recordings. Yes, of course. If you want to hear my my slowly dying voice, you can hear you can hear it. But all of these will be provided later on. Okay. Shall we conclude here or any more questions? Otherwise, I'll be at the conference, even at the boat party and the dinner. You can come up to me. We can talk more about variation algorithms or my works. I've applied these algorithms just to give you ideas to thermal state preparation, to entanglement classification or calculation of entanglement, to finding ground states of fermionic systems or even topological models. So these might be a lot of new words, but if you hear any of these fancy sounding words and say, ah, this looks interesting, come up and speak to me. Okay? Thank you guys. Thanks for listening.